Hi, everyone. My name is Jace Warren, and first of all, I just want to say it's an honor to speak to you all today and have the opportunity to participate in this conference. And over the course of this presentation, I will be speaking on replacing a billion-plus record per day Cassandra cluster with Elixir and SQLite. Apologies for that mouthful of a title. One second. Let me go to there we go. So to tell you all a little bit about myself, I was born and raised near Salt Lake City, Utah, and it can get covered in its fair share of smoke as well, especially during the California wildfire season. The smoke makes its way over the mountains into our valley, and it kind of gets trapped there. Overall, though, it's a beautiful place, mountains, wonderful skiing, wonderful people. MPEX hosted there back in 2022, I believe. It's a wonderful place. Highly encourage you all to visit. But right now, I call Dallas, Texas home. Wonderful place as well. I've been in the industry for around 12 years. As far as social media goes, I don't really do much there. However, if you do want to find me, here are some of my social links. Like my talk, very boring content there. So to gain a better understanding of what I'll be speaking about today, it helps to have some background about Savi Solutions as a whole. And we are a small engineering team that does a lot of things centralized around video. We provide the customers you see here and many more with a VMS or video management system, which enables them to easily access, download, play video in the cloud, for all their various locations. We also do a lot of interesting things with captured video, like tying it to point-of-sale data to provide high-risk transaction audit reports. We provide an event search, which allows customers to filter and view clips for all events that happen throughout the day in their store. We do alarms, and honestly, we just do so much more. But as a quick aside, we are hiring, so if any of this looks fun to you, challenging, interesting, please feel free to reach out to us. We're always looking for talented engineers who want to engage in these fun problems. So I don't want to go into too much detail about video streaming at scale, but I do want to share enough context to show why we have such a large database in the first place. Video streaming as a whole is considered by many to be quite complex. In the video streaming world, especially if you work with surveillance and closed-circuit television, CCTV cameras, it's not as simple as pulling or pushing video from a video camera, NVR, turning around and then playing that in a browser. Generally, the streaming protocols used in cameras and NVRs will not work that way. And so as a result, there are usually multiple stages at play here. Initially, there's a first-mile delivery stage that involves capturing content from the camera to an encoder, which in turn transmits to the video over a network to a series of intermediary processes and servers. At the server layer, then we can do like some transcoding, some transmuxing, producing multiple bitrate outputs, things like that, thumbnail generation, CDN population. And once the video is prepared and ready for the customer, and when we deliver it to their device, that's essentially the last mile delivery stage. So at Savi, we mainly work with 3 streaming protocols. As far as the first mile delivery stage goes and surveillance goes, most CCTV cameras and NVRs have standardized around RTSP protocol. So if a customer is willing to grant us external access to their network, we can reach out to the individual camera, NVR, and we can pull the video that way into our cloud platform. However, in cases where the customer doesn't want to open up their network, we have an edge device that we can ship out to their location, and it can kind of communicate with the cameras that way behind their firewall via the RTSP protocol, then turn around and push that video out to our cloud platform via the RTMP protocol. Now, as far as the last mile delivery stage goes, once it reaches our platform, it of course gets transmuxed and converted for HLS playback. So let's talk about the HLS protocol. HLS stands for HTTP Live Streaming. It was developed and released by Apple in 2009, and it's arguably the most widely used last mile stage. What's nice with HLS is your video will likely play on any device, and through adaptive bitrate streaming, you can increase or decrease video quality depending on network conditions without interrupting your playback. So how it generally works is that the video gets streamed into our platform, it gets segmented into chunks, a few seconds in length maybe. From there, an index file or playlist gets constructed consisting of the video segment files in the order they came in. If there are multiple bit rates or qualities, then there can be a top-level multivariant playlist that then describes and points to the child variant playlists with their various qualities and their resultant media segments. There's also different types of playlists. Mainly the two that we work with is a live or sliding window playlist, and how that works is it's basically like an open playlist without a closing tag where we just continually append video segments, URLs to the media files, and as the video transpires, we're basically removing segments as it moves forward. And then there's also like a video on demand scenario where we're basically grabbing all of the segments at once, and we just allow the video player to kind of play the video from beginning to end that way. All right, so as mentioned before, as video comes into our platform, it gets broken into segments. For live or near real-time playback scenarios, we try to keep the segments between 1 to 4 seconds. This helps us to achieve lower latency form of playback. And we also generate our playlists dynamically, which is nice. What that allows us to do is, let's say we have a video stream coming through, and it's coming through in 1 second segment chunks. The second 3 of those segments become available and playable, we can then turn around and dynamically generate a playlist, add the segments to that playlist, and we can get close to around 3 seconds of latency for our customer, which is nice. I mean, obviously, that value changes if the customer, due to customer constraints, we have to basically scope that to 4-second segments and things like that. And even though we can achieve this degree of low latency, we generally aren't that aggressive with it, but it is nice to have it, that functionality when necessary. Another thing worth noting here, for non-live or non-real-time playback, we don't really keep our segments at 1 to 4 seconds in the long term. As long as we're a playlist or something, or our segments are a couple minutes away from real time, we can just as easily load 30 to 60 second segments in an HLS playlist. So by generating larger segments in parallel, we can essentially store 87 to 98% less overall records in our database. So those 1 to 4 second segments, we can basically clear those out once they're far enough away from real time, and then we're just left with the much smaller storage footprint of the 30 to 60 second segments. So how does this relate to Cassandra? Well, basically, as each segment gets processed and each media file gets stored, we then also need to store the segment file metadata in some sort of a database that we can query regularly in order to generate these HLS playlists. We also do a lot of thumbnail generation. In some cases, we have to concatenate video segments together to make MP4 downloadable files for police reports and various other things. The list goes on and on. So we just needed a database that could handle HLS type of workflows and a high volume of it. So how many records are we talking here? Well, based on the previous slide, a single stream can produce between 23 to 89,000 segment records per day. Then if the customer wants to have maybe 2 or 3 bit rates, we have to basically apply that multiplier to that record count. So long story short, for our use case, we basically need to process a large volume of data. So when factoring in, back when we set out to, for us basically, but back when we set out to build our video streaming platform, before that we were using a third-party provider to manage video for us. Unfortunately, they didn't have great uptime, and they were a little expensive. And so that's why we set out to build a video streaming platform in the first place. But at that point, we already had quite a few customers. And so when we factored in our current customer count per day, we figured we would need a database that could process over 1 billion records per day and process well over 10K or 20K writes per second, over 10K inserts, 10K deletes when we factor in our 1 to 4 second segment cleanup, and then also 10K reads, because as video's being streamed, it's almost always being watched at least once. And so in the semi-long term, based off of our growth trends as a company, we also knew that we were going to have to process 100,000 plus writes per second in the long term, not too distant long term. Now, this scale might not be big for some. I mean, we're definitely not getting anywhere near Netflix scale, but for us, this was a big ask. We have a very small engineering team. But yeah, so Cassandra enters the chat. So why Cassandra? What is Cassandra? Well, it's a database introduced by Facebook in 2008. They built it to help scale their inbox search. It's based on the Dynamo paper written by a group of engineers behind the Amazon Dynamo database, also known to scale. It's a column-oriented database which stores data tables by column rather than row, which is great for our use case because we never have to query segment records across more than one stream. When we're generating a playlist, we're generating it for one stream at a time or one bit rate at a time. And so it's highly performant, meaning it should, in theory, be able to handle 20 to 100,000 plus writes per second, those scenarios I mentioned earlier. And then there's just so many case studies. There's Netflix back in 2011 performing 1 million writes per second, which makes our case look very small. Another nice thing, it scales linearly. If we have 3 nodes doing 15,000 writes per second each, that's 45,000 writes per second in total. We can just add another node, and then we're basically doing 60. Sign me up. And so fault tolerant, it's great that if a node gets destroyed, it generally has a replication strategy where it's storing copies of each record on other nodes. That node gets destroyed, you can basically remount another or redeploy another node, and then the data will get distributed across it, so it's great in that regard. And then I mentioned earlier that we're deleting our 1 to 4 second segments regularly once they get past a certain point from real time. Cassandra supports time to live, or like TTL, time to live. And so we can, as we insert a record, we can give it an expiration time period, which is also nice because for each of our customers, we, as they configure a stream or set up a stream, we give them options as far as like how long they want to retain that stream footage for, be it 180 days, 30 days, it's configurable in that regard. And so lastly, there is the boring software manifesto. We've all heard of that. As software developers, we are tired of the false claims made by evangelists of the latest and greatest technology. We will no longer confront them with their lack of understanding of computer science fundamentals. It goes on and on. I won't read the whole thing, but you get the gist of things. We're a small team. We don't have the luxury to gamble on new, hyped, volatile technology. And so surely Cassandra can be classified as boring technology by this point. And so all in all, we figured it was worth trying out, moving forward with. And so we developed a plan. So Cassandra, like I said, Cassandra seemed great. Based on our limited knowledge and due diligence, we figured we could simply plug it into our architecture, more or less the same way you plug in like a Postgres database, as seen in the example there. But we needed to thoroughly vet it out. And so we came up with the following plan. So basically, we wanted to design a schema. We're not experts. You're going to hear me say that a lot. Perform stress tests on that to make sure it actually performs in Cassandra. And then, like I said, we're not experts. We wanted to use a third-party vendor. Small team. We don't need another technology to manage. And then we needed to implement a disaster recovery plan because we're in the surveillance space. Video has to always be on. The customer expects that. And then load test it. We wanted to make sure it would last for our 5-year use case. And so then if all of that went well, we'd basically do a full rollout. Also, I need to add a disclaimer here. This plan suffers from hindsight bias. We actually didn't end up adding the platform load test step until after a failed alpha release. That being said, this was more or less the path we took to a rollout. All right, so we got to work on a segment schema. Designing a schema that works well with Cassandra was a very iterative process. We'd think we had a good design, then we'd stress test it and we'd find out we had a terrible design. And so it was basically constantly redesigning, stress testing, redesigning, stress testing. Ultimately, we tried to follow best practices as we understood them. We set up a simple denormalized table structure. We're not doing any relational type of structures here. We designed our composite partition key, seen there with stream ID and ABR, and then those fields. We designed that in a way to avoid uneven data distribution and have pretty consistent partition sizes. We're not going to have lopsided like disk storage here. We also made sure all partitions were well within the 10 to 100 megabyte size recommendation. We ensured all queries would resolve to at most a single partition. We were avoiding hotspots and different things like that. Overall, this is the schema we landed on, and I'm sure there are much better approaches. However, we did cross-reference this design with consultants, and we did get positive feedback and confirmation that this was basically a good pattern to proceed with. So we did. We went on to the next phase. Like I said, it was an iterative process going back and forth, tweaking the schema. But all in all, we aimed for a 5-year growth scenario with some buffer in terms of throughput. Whenever we'd perform a stress test, we'd start with 3 nodes. We'd get it to a certain throughput, and then we'd slowly add more nodes to the cluster just to see how it would perform. We used a replication factor of 3, meaning each record was backed up to secondary nodes. As far as performing the stress test, we used the Cassandra stress tool, which is great at determining how a schema performs. We used a mix flag with it so that it was doing a mixed load of reads and writes to give us a better idea, a more realistic type of workload. And all in all, we were pretty happy with our result. We were able to get a Cassandra cluster that was getting around 15,000 writes per node, which would work for us and our long-term goals. And like we said earlier, Cassandra has the ability to scale linearly, and so as we would grow, we could add new nodes to our Cassandra cluster, and it could grow with us. Again, we're a small team. We're not Cassandra experts. We had enough on our plates already between all our different product offerings and features. We were hopeful that we could hire some Cassandra experts to manage things for us. Unfortunately, we did have limited third-party options due to cloud provider lock-in, so we were forced to use a very specific cloud provider that just didn't have a lot of options of people that worked with that cloud provider. But we were able to find one, and fortunately, they had Terraform support, which was great because that fit perfectly into our disaster recovery plan. And so, like I said, our customers expect camera streams to always be up and accessible. Terrible things can happen when surveillance systems go down. In fact, one customer had an incident recently where a disgruntled employee waited until after hours to come in and steal thousands of dollars of inventory and cash from the store. Now, normally, in those types of scenarios, a culprit will come in, steal, and then they'll go and destroy the NVR. And normally, that would be enough to get away with the crime. However, in this particular situation, our software was running at that location and streaming the footage out to our cloud platform in real time. And so after the theft occurred, the customer did some investigative work. They went into our video player, and they watched as the employee didn't even put on a mask because he was so sure he was going to get away with it. Went from register to register, grabbed a bunch of inventory, then went up to the NVR, shot it with a shotgun. Before he destroyed the NVR, he even looked at the camera. And it was streamed out in real time before the stream went dead. And so now, the point in telling you all about that incident is that as developers, we make mistakes and accidents happen. As discussed in Heidi's talk today, distributed systems are difficult and go down. Any downtime brings about a huge amount of vulnerability to our customers as well, or to our customers, and so we wanted to invest in a DR plan to ensure that we can get back online as quick as possible. And so as far as approaches go, we decided to go with an infrastructure as code approach where we define our network, servers, load balancers, et cetera, as code. The beautiful thing about that is incremental infrastructure changes can be managed with Git, reviewed by members of your team, and then applied. As far as the tools we use, we mostly use Terraform and Ansible workflows and execute them via GitHub actions. Ansible's fine, but Terraform is nice because we can generate a plan visualize the changes before they get applied. And so if you want to get super fancy with your CI workflows, every time you open up a PR, you can basically have a CI step that will generate a Terraform plan, post it to your PR, your newly opened PR as a comment, and then your team can view that plan in real time before, or just in the PR before reviewing or approving the PR, which is kind of nice. But yeah, really the big idea here is our architecture and platform had to be easily reproducible, so we could do load tests. So thanks to that disaster recovery investment, load testing our platform became a breeze. As I mentioned a moment ago, our entire architecture is completely and autonomously reproducible. This means that we can spin up a one-to-one environment with our customer-facing production app on every single pull request, and that's what we do. And so in software development, every new deploy or release is essentially a minefield. And our jobs become so much easier when we can then detect and diffuse those mines long before the customer does, or it blows up in the customer's face. And so in the surveillance space, I personally have had enough late nights chasing down bugs in fear of losing a customer for more than one lifetime. And so thanks to this per PR opt-in load test setup, we haven't really had to spend too many late nights chasing down stream bugs and getting them back online and things of that nature. And so how does this work? It's pretty simple. We have a resource group specific namespace, and we can trigger that via a workflow dispatch in GitHub, via like a GitHub Actions. You go into GitHub Actions, you select your workflow, and it has a form. We have a resource group name. You can put in your PR number, you can put in whatever you want, you can select whatever branch you want, and it will deploy a one-to-one environment with our production grade like video streaming platform. And we don't do a staging environment just because staging very rarely actually ends up being a one-to-one with production. And in this case, we sampled different customer camera streams, and we came out with a good distribution of streams that we could load test across our like preview environment workflow. And so we didn't really feel like we needed a staging environment at this point, and it just would have been a waste of money. Also, running a video streaming platform is expensive. There's a lot of concurrent services that are running, working together in parallel, especially if you're running a Cassandra cluster with it. And so, yeah, we just continually iterated until we passed our 5-year use case. And so we just, kind of like our schema design, we make changes, test it until we got to this level. And after that, everything worked as expected. We had a very nice deploy. We had a P99 of less than 200 milliseconds when we were querying our Cassandra cluster. Iterative changes in our preview environments were working great as expected. Every time there was like a new major third or like dependency release, spin up a preview environment, load test it. Anytime there's a major code change, it was really nice. And so Cassandra was absolutely the least of our concerns at this point. But 6 months later, again, you've got to be sick of hearing this at this point. We're not Cassandra experts. And so we started to experience some pretty significant third-party issues. And so, during one particular, sorry, I'm messing this up, but yeah, so our cloud provider kept asking us to switch to a different, our third-party Cassandra provider kept asking us to switch to a different cloud provider because that cloud provider didn't provide enough availability zones. That was basically the beginning of our issues. And then we opened up an issue with them to upgrade to a Cassandra version 4 because version 3 was no longer going to be supported by them. And then when that happened, even though they were managing it, our Cassandra cluster got locked, and only half of it was updated, and the problems just continued. Node migrations would rarely succeed if we needed to like cycle a server or something like that. In our preview environments, it even got to the point where we couldn't even spin up a new Cassandra cluster in our target cloud environments because they were out of space, they said, with that specific region with that cloud provider. Or they out of resources. They had used all of their resources that were allotted to them by that cloud provider. And just different things like that. Our disk began to greatly outpace the amount of segment data we were actually storing in it. And I'm not a Cassandra expert. I wish I could have dove into the weeds more. But that's basically what we were getting fed by them. And our costs just began to balloon. We were on track to pay for over $80,000 a year for our Cassandra cluster. And it was beginning to affect our customers. So we needed to get off of it. And so we had some replacement considerations. We could become Cassandra or Scylla experts, but we barely had time to do the work that was put in front of us to begin with. And so we could do some stuff with Postgres, like a Citus flavor or a timescale flavor. There's endless amount of options. We were using Prometheus for our telemetry with Promex, which is a great library. Had plenty of options, but ultimately we had a different plan in mind. We didn't want to do any of that. And so we were always actually planning on replacing Cassandra since the beginning. We had to adhere to the boring manifesto, but in our hearts, we didn't want to. And so we didn't think it would be this soon, but we're using Elixir in the Beam, and we have a distributed, our cluster communicates with each other via distributed Erlang. We're aware of every single node, its location, its status, its capacity, the work that is happening there. All of our stream workloads are basically deterministic. And so we were primed for an embedded database approach. And so we swapped the boring software manifesto for the programmer's credo, which is we do these things not because they are easy, but because we thought they were going to be easy. And so that's a quote from our CTO. Had to throw it in there. It's his favorite quote. And so why SQLite, So we were originally looking at Manesia, ETS, DETS, and others. However, around that same time, SQLite was making a lot of waves through blog posts, podcasts, and Twitter, thanks to the great work of Ben Johnson, the creator of Lightstream, and the wonderful blog posts and overall knowledge sharing from the Fly.io organization. And so we had to see what all the noise was about. And so for those of you who don't know about Lightstream, it was originally created to kind of solve some disaster recovery scenarios with SQLite because it's basically a file. If your server goes down, it's gone too. However, it's also great at bringing distributed functionality to SQLite with file replication, backups, and more. So if you haven't checked it out already, I highly recommend you do. But SQLite doesn't scale, right? There's only a single writer. It's actually quite performant. SQLite will easily, according to the SQLite docs, it will easily do 50,000 or more insert statements per second on an average desktop computer. Though it will only do a few dozen transactions per second if you want to do a transaction type of interaction, but we didn't need transactions for our workflow, so it was basically good for us. And then as recent as 2010, they've also introduced a write-ahead log. For those of you that don't know, it's a journaling mode, which writes database pages in a separate WAL file first, before later copying and applying that to the main database file. And so this actually helps with reads. And so also a nice feature about SQLite is you can basically have unlimited simultaneous readers or reads, as many as you have threads, basically. And so it can read off of that WAL file, get the data there if it's accessible and quick enough. If it doesn't find it there, it can go to the actual database file itself. And so lots of improvements that way. And so SQLite is really improving. So we developed a new replacement plan. And it's very similar to, it's basically the same as our Cassandra workflow, So we wanted to perform stress tests, like we were hearing great things about SQLite, but of course we need to validate that, right? And we needed to do some pretty dramatic changes around our Ecto repo setup. And we knew that we were going to have to do partitioning to get the scalability we'd need, where we basically we partition and by having separate SQLite files. And so we knew that Ecto migrations were going to be tricky. And then with that also comes some cross-partition querying implementation logic. We're not dealing with Postgres where it's really easy to create partitions and then query across them. We have to add that logic in our code. And then also TTL support, we need to delete a lot of records. And so we had to develop some functionality around that. And then we could use our same end-to-end load test framework that we were using before, but now we just don't have to do it with Cassandra. And then, of course, we had to do a zero-downtime migration because video has to always be up, right? And so, again, because we were using distributed Erlang to break down our big Cassandra database into many small SQLite databases, we don't really have to push SQLite to its limits on a per-server basis. And like I said earlier, the SQLite docs advertise that it's capable of 50,000 or more inserts per second on an average desktop computer. That was more than enough for our per-server use case. And you'll find much more impressive examples in the wild than us here. Like I said, we're not a special use case. You've got a company. Oh man, let's see. You've got here. I think I had it in a past slide. Sorry, I think I messed that up. But yeah, you've got Expensify. They're doing 4 million queries per second on a single node, and so that's crazy. So yeah, for this was basically a non-event for us. We tested it for our workload well under the 50,000 inserts per second threshold, passed with flying colors. Yeah, I mean, deletes were a little bit slow once we got to a certain database file size, and so we did. That was further confirmation that we did need to partition by file. And so what we originally were doing in our Cassandra cluster is we were essentially partitioning we were doing a list-based partition based off of our stream ID. But in our SQLite implementation, it made a lot more sense to do a range-based partition, because then we can do bulk upserts. If we're partitioning by a single date, all segments that come in for that date, we can bulk insert them all together. As far as deletes go, as a partition or a date-based partition ages, we can apply a delete operation to that file at least once as it ages. And so really it gives us the ability to do deletes in constant time. And once a file gets past 180 days or whatever our max retention period threshold is, we can just drop the file and delete it, which is nice. And so as far as our Ecto repo setup goes, one thing that we knew that we were going to have to do is have separate writer and reader repo, just because SQLite does only support a single writer. And so if you try to do 2 writes at the same time, you're going to get an error message back that's saying it's busy, right? And so we needed to make sure that we would avoid that as much as possible in our application. So we created a single writer. We limited the pool size, so we were only ever basically having 1 writer accessible at once. As far as reads go, like I said earlier, you can have virtually unlimited simultaneous readers. So for our read replica, essentially we had a large pool size. And then Ecto SQLite, which is kind of under the hood, it pairs with Ecto. It comes with some great configs. It enables the wall file by default. It increases some memory adjustments, and it's honestly a really great start, and we had to make very few adjustments to that actual config from day one. Basically just had to adjust the pool size. And then we did have some back-end gen stage workflows. We had a lot of segment metadata records that we're processing in real time. We just had to adjust the concurrency of those workers as well. And then multi-database support with put dynamic repo. So this is really the magic here. This is what made our job so easy. I can't say enough good things about Ecto put dynamic repo. And so what it allows you to do is you can start multiple connections using you can basically define your repo once, and you can start multiple connections using that same repo, and you can use that same repo and you can connect to multiple databases. You can continually swap out paths to your SQLite file and access multiple databases. And so how it works is when you go to execute a query or something for that repo, you just set the dynamic repo to a specific process that points at a specific SQLite file, and then it executes across the next series of interactions in your app. And so in our use case, or typically, if you look at like the Ecto documentation, they say it's typically used to perform short-lived database connections. And so you're basically just, the only time you have to access the data set, you spin up the process. The second you're done accessing the data set, then you basically delete the process. But in our use case, when we're viewing live video, we can have multiple people viewing live video at the same time, and so we need to keep those processes around. However, as we've noticed, the older a partition gets and the further away we get from real time, the access to our partition drops off significantly. And so we don't want to keep those repo processes up for too long. They basically have like an expiration where they become stale, and it's not worth it for us to keep them around. And so we basically switched over to using a dynamic supervisor and registry pattern. And so how does this affect your queries? So basically what you're doing is not much really changes. So we can encapsulate all of the partition connection and put dynamic repo logic in a public function defined in our repo. And here I provided a simple insert all upsert scenario targeting a single writer pool right here. And so basically we at my repo, as we see here, I've defined a function called with dynamic repo. And in it, I allow for a couple parameters where you can pass the date, which will essentially direct to the SQLite database partition, and then you can do a writer if you want to access your single writer, or in the below example, we have a reader if you want to do a request across your reader pool. And so it's as simple as basically just wrapping your normal Ecto query in an encapsulated function that you can define at your repo layer. So how does that look at the repo layer? And so here we basically just define our dynamic repo, and this is just a simple example. This isn't exactly how we have it set up in our code base, but what we're doing here is when we receive a date and we have a type of interaction we want to happen, whether it's a write or a read, we basically find or create that repo process with our dynamic supervisor and registry. And so right here, before you saw the wrapping with dynamic repo, we have a callback before it executes the callback and before it sets the repo process targeting that specific database file. It actually invokes this find or create repo function, which passes the date, the type, and based off of that, we can resolve to a read-specific process if it exists, or a write-specific process in our existing registry using the via tuple. And if it exists, then great. We can just return that PID. We're good to go. If it doesn't exist, it gets created, and we still get the PID. We can perform the operation we want from that point on. And seen in the bottom, in our case, we actually do it this way. We have different configs for our write repo versus our read replica repo. You can just define that within your config, reference it here, and dynamically swap out the SQLite path and any other specific like Ecto configuration values you want to, which is nice. So here it is all together. Sorry if this is kind of small. It's pretty simple. This is more or less all you'd really need. So you have your repo that you've defined here. We just have our registry dynamic supervisor defined here. We don't even have to do a reference file. We can just define it in our application children list, And then here is the example that we were looking at earlier. Pretty simple, pretty straightforward. This doesn't include like the installation of the dependencies, obviously, and the config values, but this is a pretty simple implementation to dynamically swap out SQLite files and have a writer and a reader. So what about running dynamic Ecto migrations? Like I said, we're generating a new partition on a daily basis, and so we have new partitions getting generated constantly. And so running migrations is easy. It's the same thing as we were doing a write type of query or we were doing a read type of query. We basically just use that same encapsulated function defined at the repo layer, and then we just execute our migration. The only key difference here is we're passing the process ID from the dynamic repo callback that we pulled from our dynamic supervisor and registry, and we pass it to Ecto Migrator so it knows which repo process to execute the migrations against. That's basically the only difference there. All right. Yeah, so I'm going to rush through this a little bit. I'm running out of time. Sorry about that. So migrations work great. We have different scenarios that we need to account for, development environments, long-running scenarios if an app's just running for a long time, and deploys. And so how we get around that is we just have a Ecto setup partitions task that we can run before we run like mix Ecto reset, like just those different types of operations, and so forth. We can have a nightly cron job that will generate the partitions for the oncoming week, things like that. There's a simpler approach that we could have done instead of all these different steps, but we could have done a hydrator method or a hydrator process that does the same thing, but that worked for us at the time. Cross-partition querying is easy. You just take from the query params the dates, like if you're doing a time-based range query on our segments, we just extract that, and then we can execute each query independently, and then we basically just normalize and sort the results and put them all back together. Really easy. We isolate it to our context layer because the rest of our app shouldn't have to worry about this. TTL support, really easy as well. For 1 to 4 second segments, we just have a cron job that runs every 5 minutes. It deletes all 1 to 4 segments for the past like 5 minutes. As far as the 30 to 60 segments, we actually have a gen server that will run nightly, and it applies retention period deletes on our database file once as they age. So like if we have a 30-day retention period, we're only ever going to execute that 30-day retention period against that file once when that file ages to that point in time. And so we can do efficient deletes across all of our different partition files as they grow old, I guess. And then as a file gets past a certain point, we just delete it, and then we can also drop the processes as well, the repo processes. So load tests, we basically just swapped out Cassandra for SQLite. Everything went great. As far as the zero-downtime migrations, it was really simple. So we basically created the new DB tables. That was step 1. And then step 2 was basically just doing concurrent writes to our SQLite file, the same that we're writing to our Cassandra file. But we keep the reads going to generate our HLS playlist from the Cassandra database. And so step 3 is basically just backfilling the data from Cassandra to our individual SQLite partition files. And that's really easy because we have distributed airlane cluster, our workloads are deterministic, and so each node is essentially aware of itself what streams it should be monitoring or managing, I guess. And so after that, once we perform the backfill, then we just swap the reads over from the Cassandra instance to the SQLite instances. And then after that, we just drop Cassandra. It's gone. So how did it go? Zero downtime deploy went perfect. When we first released, we had a P99 of less than 50 milliseconds, which is great. Our average query time is actually less than 5 milliseconds. On average, it's around 2 to 3 milliseconds. Customers immediately noticed improvements in our video streaming platform. And then, of course, we just we're doing embedded SQLite databases across our already pre-existing Elixir applications and servers. So this added 0 cost to our infrastructure. And then we could just delete Cassandra. That cost went away. So 9 months later, we had some growing pains, like I said. Hindsight bias, we actually sacrificed doing the partitioning later so we could get off of Cassandra sooner. So we just deployed with a single SQLite file, and then a month later then basically did the partition SQLite files. So there was some latency there, but it still was way better than Cassandra. Seg faults, so with SQLite, it's using a NIF implementation, and so if you have a slow query, there are some edge cases where it can basically create a seg fault, and that takes down your entire Elixir application. So make sure your queries are in good shape. And then we had to do some volume mount adjustments for our SQLite files, things like that. But still, 9 months later, our P99 is less than 50 milliseconds. Our P99s haven't changed, basically, and our average query times haven't changed. And we continue to have customers come out of the woodwork and say, wow, your platform is so fast, or we're doing a demo for a customer, and they're just blown away by how fast our video loads, and they say, wow, I see why I have to move to the cloud. And so thank you. Thank you for your patience. It was a lot to cover. Appreciate it.